Figure 6 shows a graph of current against potential difference for an electrical component. So you can see here we've got, well, I know what this is immediately, it's a diode. So anything which is like flat here then increases is a diode. The other ones you need to know is a fixed resistor, which is a straight line. So there's a directly proportional relationship. So if you double voltage, you double current. You double the push, you double the flow of electricity. And this is a filament bulb, like a lamp you use in a lab. Now, with that, you have a directly proportional relationship up to a point. Up to this point, it's a straight line. So if you double voltage, you double current. But after a while, the resistance increases and current decreases because of heating. So it's affected by heating. So you get this this leveling off bit here, where increasing voltage doesn't have a massive impact on current. Just be aware that these graphs go in the other direction as well, so it means that you just switch the pins around and now the electricity is flowing in the other direction. So it's exactly the same thing, it just means now the circuit is in reverse. So rather than the electricity flowing around this way, it's now flowing around this way. So that's why you get these going into the negative. Don't get confused by that. You're really only explaining one side of these. However, with a diode, it's slightly different, because a diode is a circuit component that only allows electricity to flow in one direction. You don't have to ever explain this bit. This bit's really complicated. All you have to recognize with a diode graph is it only increases in one direction, and that's because it does not allow electricity to flow in the other direction, and that's why I know this is a diode. So that's why I've put this here. A diode, by the way, just in case you ever need to know, has a circuit component symbol like that. And diodes are useful in circuit boards and things like that, where you've got to carefully control the direction of current flow. Next, an easy calculation. A lamp is connected to a potential difference of 0.24 volts. That's a voltage. The current in the lamp is 0.12 amps. Calculate the power. So this is really easy. You shouldn't lose marks here. It says power equals current times voltage. You need to know that I is current. Maybe that's the only area where you might be thrown. So you just do 0.12 times 0.24 and you get 0.0288 watts. The potential difference, the voltage, is changed to 0.3 volts. The current in the lamp is now 0.13 amps. The lamp is switched on for 35 seconds. Calculate the energy that is transferred in this time. Select an equation from the list of equations at the end of this paper. So what you're looking for is you turn to the back of the paper and you'll see a sheet which looks like this. You just have to marry up the right equation with what's given here. So you've got voltage or potential difference, current, energy transfer, that's what we're trying to work out, and time. So what has these things? So let's look for energy transfer. We can see energy transferred here, current upon potential difference in time. So there you have it, really easy as long as you look at the back. So we just have to do what it tells us to do. We have to do 0.3, which is our potential difference, 0.3 volts potential difference, times 0.13 amps, which is current, and times 35 seconds, which is time. And then you have 1.365 joules as the answer. The current in the lamp stays at 0.13 amps. Calculate the charge that flows through the lamp in 35 seconds. Use the equation charge equals current times time. So again, it's pretty easy. Current, time, and you'll work out charge. So 0.13 amps times 35 seconds is 4.55 coulombs. That's the unit of charge. So a lot of people worry about physics exams thinking they'll be the hardest, but in some ways they can be the easiest because they give you so much information. All you have to do is read the question carefully and just plug in the right figures and you get the answers. So physics can actually be the easiest paper sometimes. The student measures the current in the lamp for several values of potential difference voltage across the lamp. Here you see the results, 0.6, 0.12, 0.18 and so on. You can see the current increasing as well. Now, let's just have a look at this before we move on. You can see that it's increasing, and then it's starting to decrease, well, not decrease, but the increase is getting less, and then it's leveling off. So we're getting this shape here, not this shape here. So just be aware of that, and I'm sure that will be referenced in the question coming up. Always take time to look at a table and see the pattern. A student uses the results in figure 7 to write this conclusion. As a potential difference, the voltage across the lamp increases, the current in the lamp increases, and the relationship is directly proportional. Comment on the student's conclusion. Up to a point, they're right. Up to a point, they're sort of right. You have this relationship here, where you can see it is straight for a bit. But then, after a while, it levels off. So increasing the potential difference doesn't increase the current, it stops increasing. So for 3 marks, what you'd have to recognise here is, firstly, they're right in the sense that current does increase with potential difference, at least at first, but it's not a directly proportional relationship. You can see that the current reaches a constant value. So while it does increase, even here, you can have a look, it's not directly proportional. So this is doubling here, this change here is doubling, but this isn't doubling. And again, this is going up, this is now tripling from here to here, this isn't tripling here. So you can see it's not a directly proportional relationship at all.